This video is about circle theorems. We have a circle, and let's say this is our center O, right? So this is the diameter of the circle. So circle theorems basically are a bunch of rules that we use, to find angles relating to, something in a circle. Now, what's interesting is we can prove this. These are just not some random rules. These have been proven. So for our first rule, okay, we have an angle right here at the circumference, angle x, let's say, right. Now we have another angle here on the circumference. Now you will notice that both of these cover the same exact sector, the same exact arc, not sector. So if two angles at the circumference of the same circle cover the same arc, right? So one arm of one angle and another and an arm of the other angle, and the other arm of an angle as corresponds to the other arm of the other angle, then both would be equal. So this, let's say this was angle, okay, A, B, this is C and D. So therefore angle ACB is equal to angle ADB, right? So for our first rule, an angle from the same arc are equal, or angles from the same arc. That's our rule number one. Now we're going to go a little further with this. So okay, now if we were to take the same angle, ADB, and using the same points make an angle with the center of the circle. This new angle right here, you just erase some of these lines so you can get a better picture. Yep, this angle right here is going to be twice the angle at the center, at the circumference. So the angle at the center is twice the angle at the circumference. So now we're going to look at the next set of rules. The next rule pertains to cyclic quadrilaterals. So a shape is considered cyclic if all its points lie on the circumference of a circle, of the same circle, right? All of its points lie on the circumference of the circle. So this is a cyclic quadrilateral, whereas this, you know, um, this right here wouldn't be a cyclic quadrilateral because the fourth point here isn't on the circumference. So please remember, all points of the polygon need to be on the circumference for it to be considered cyclic. Alright, so now that we've established what a cyclic quadrilateral is, I could draw. So we're going to draw, it's a very, very simple proof, this. So it relies on the second rule, which we've already proven. So let's call this angle A. Now, if angle A here, angle A, if this is angle A, then the angle at the center is going to be twice the angle at the circumference. Now you might think that this is the angle at the center, but it's actually this. This would be 2A. And it needs to be facing the same direction. It needs to be corresponding. Right? Now let's call this B. And again, same rule. So that would be 2B. Now we know from angles around a point that the angles around a point is equal to 360 degrees, add up to 360. So here 2a plus 2b is equal to 360 degrees, right? And that would just mean that a plus b, because we take 2 times of a plus b is equal to 360, and that's a plus b is equal to 180 degrees. And then, so you get this plus this is equal to 180 degrees. And that's our third rule. Opposite angles in a cyclic quadrilateral are supplementary. Right? Now imagine this is the diameter of the circle, right? And this is, let's say, the center O in the circle. So that makes this into two semicircles, right? Now, if I were to draw a triangle with the diameter as the base, regardless of what point I draw it from, the fourth theorem states that the angle in a semicircle is equal to 90 degrees. So what that means is this apex angle here is a right angle, and this forms a right angle triangle. Right? Even if I, let's say, make a triangle here, here, it's all going to be 90 degrees. Now to prove it, it's fairly simple. Let's choose one triangle, this one, right? So we have a triangle here, and the first thing we're going to do is draw a line. This is O, A, B, C. We're going to connect O and B. Right? So now we have two triangles, OAB and OBC. Now you might also notice that OB, OA, and OC are radii. Right? OB, OA, and OC, these are radii. So they're all equal. Now if they're equal, that makes this angle B and angle C, angle OBC and angle OCB equal, and angle OBA and angle OAB equal. So let's call this X. Okay. Let's ignore all other angles. Oops. Yeah. Okay. So if this is X, then this is obviously going to be X, and this would be 180 minus 2x. You know, angles in a triangle, the sum of angles in a triangle is equal to 180 degrees. That property. And now since this is a linear pair, AOB and BOC are a linear pair, this would be 180 minus of 180 minus 2x. So now the 180 and 180 would cancel, and the minus and minus is going to become a plus. So you're going to get 2x. And now to find the base angle, you're going to do 180 minus 2x yet again, but you're going to divide it by 2, right? Because there's two angles that need to share. So that's going to be 2 times of 90 minus x by 2, and then this 2 and 2 will cancel, so you have 90 minus x and 90 minus x. Now angle AOB, ABC, sorry, is very simply ABO plus OBC, and ABO is nothing but 90 minus x, and OBC is just x, so minus x and plus x would cancel, and you get angle ABC is equal to 90 degrees. So that's our fourth theorem. The angles in a the angle in a semicircle is equal to 90 degrees. Okay, so now we're going to look at our next theorem, which involves tangents. So tangents are basically any line that touches the circumference of the circle at one point and one point only. To us, it may seem like it touches the a circle at multiple points, but in fact it touches circle at merely one point. Right, so this is a tangent and it will touch the circle here. Okay, so our next theorem says that the angle between a radius and a tangent is always going to be 90 degrees. Right? This is going to be 90 degrees. This is our setup for proving this. See, the definition of radius is that it's the shortest distance to circumference of the circle. But if, let's say, angle ACO was not a 90-degree angle, right? It's not a 90-degree angle. Then some other length would have to be the shortest distance to the circle. That would have to be a 90-degree angle, because that's the shortest distance, because tangent touches the circle at only one point, right? So shortest distance to that circumference is the radius, but any other line to the tangent would result in some extra part, as you can see here, DE. So that just proves that angle ACO is indeed the shortest distance, because there is no extra part between O and C. It touches the circle at that one point. So that's our fifth rule. Angle between a tangent and the radius is 90 degrees. Alright, now for our next rule, we're still going to be sticking with tangents. Now we're going to be looking at tangents externally. So let's say we have a point here, point A, right? Now to this circle, there's only going to be two lines, two tangents to the circle, right? Anything else would cut the circle or not touch the circle at all. So you have tangent number 1, right? And tangent number 2. And these are the only two tangents that can meet the circle, right? So if we stop at this point, right, here and here, the points that would say touch the circle, label this B and C. AC is equal to AB. They are equal in length, right? No matter what, they are always going to be equal in length. So this is useful usually in applications where this is our center O. Then you get a quadrilateral, a kite specifically. So you can use that. In order to prove that, we have our two radii OC and OB. So we're going to draw line BC, which goes something like this, and we're also going to draw line OA. Now you notice that two triangles are formed, and we know from our previous rule that this is 90 degrees and this is 90 degrees, right? My lines were straight, this would be 90 degrees. And we know that this and this is equal, right? So we know that this angle here and this angle here are equal because it's an isosceles triangle, because this side and this side is equal and they share a common side. So we have two angles that we have one angle that are equal and one pair of angles that are equal and two pairs of sides that are equal, and therefore this also this basically means that these triangles are congruent, and if they are congruent then this must be equal, right? It's related to congruency. So our Sixth rule says that tangents from an external point are equal. Now, for our last major theorem, our last theorem with proper proof is, or relevant proofs, is the alternate segment theorem. Right? So we have our triangle, let's say ABC. We have a triangle AT, right? And we also have a tangent CD. Now we know that this, if this is O, this is 90 degrees. So how we're going to prove that is, again, quite simple. We're going to go back to our first rule. So we're going to draw another angle here, right, and name this E. And sorry, oops. If this is O, I'm going to move O out of our way. This is O. We're going to draw a diameter, right? And the diameter is going to meet the circumference, and you're going to draw an angle. So now this angle X, this angle X are equal, right? And we also know that an angle at the semicircle is 90 degrees. So this is a 90-degree angle. So therefore, this angle right here, BCE, is 90 minus X, or if it, let's say it is Y plus X is equal to 90 degrees, right? And we know that these two are equal, and this angle right here is 90 minus this part right here, right? So if this angle here, if Y is 90 minus whatever this is, and we know that this is X, and Y is also equal to 90 minus X, then this is X, and therefore we proved that the angle opposite to the angle formed by the tension, or the angle in the alternate segment, is equal. So angle in the opposite segment is equal, or the alternate segment is equal. Now we have two last rules, fairly simple rules, but very unlikely to come in your examinations. However, we're going to do them all the same, because you can never be too unprepared. So first of the last two rules basically say that if there are two chords, remember chord is any two lines which don't pass through the center of the circle, right? Or it doesn't have to be. A diameter is also chord. It's a line that passes through the circle, right? From one point of the um, from one point on the circumference to the other. So if there are two um, chords and they're equal in length, right? They're perpendicular bisector, right? Um, uh, they're perpendicular distances from the center. Okay, so whatever is the perpendicular distance that goes to the center is also going to be equal, right? Fairly simple. And now the next one is a sort of extension to this. So yeah, again, we have our chord here and the perpendicular bisector, right? So now we know that this is or it's not the perpendicular bisector, but it's merely a radius. Now, if this radius happens to bisect this chord, alright, then it will do so at right angles. So it's bisected this chord, and this will definitely be a right angle, right? As long as it's a radius.